Hey there, chemistry. We have a lab to kind of go over. For anyone who is kind of like not in class or fully remote students, the lab that we did just recently was on the cooling curve of water, so related to page 60. I think it was in the notes. Pretty sure it's 60. But the cooling curve for water, what we're going to do is we're going to make our own cooling curve for water going through a phase change and then cooling down as ice. The materials were kind of straightforward, and the reason I just went ahead and kind of did the lab this way instead of showing the lab like I have been, like a hand model where you just see kind of my hands and the materials, is because this one was just kind of a lot of waiting around. It was kind of neat to see the water freeze around the thermometer, but all in all, I mean, I sat there and I waited for 7.5 minutes to get to this point, right? So, short version of what we did, we took a test tube and filled it up about an inch with water, so about that much. Took the temperature of that, so the temperature of the faucet water that I had was 22.1 degrees Celsius. Then we took a bunch of snow. I chucked some salt in there, stirred it around, got the snow really cold, and then topped off with more snow. So I had a beaker about this big, and I put the test tube right in the middle of that. So the test tube had water that was at 22.1 degrees Celsius. The snow, because of the ice, or sorry, the ice and snow, because of the salt that I mixed into it, was actually well below the freezing point of water. It was below. It was probably about -10 degrees Celsius, so very very cold. And the reason for that is we wanted the snow to be colder than the freezing point, so that the water in the test tube would freeze and then continue to get colder as a solid. Salt technically doesn't melt snow. It just makes it more difficult for water to freeze. It makes water freeze at a lower temperature than the normal freezing point. But anyway, I sat there and for, like I said, 7.5 minutes. Every 30 seconds, I took a temperature reading. So after 30 seconds, the temperature dropped to 7.1. After a minute, it dropped all the way down to 1.2. After a minute and a half, it was at zero point 0.1, and then it just like hung out at zero point 0.1 for a while. I did have this little blip at negative zero point 0.4 degrees Celsius. It dipped down a little bit. I believe that is because the thermometer was like actually taking the temperature of the glass instead of the temperature of the water. So what I did was a very scientific wiggling of the thermometer in the test tube, and it went right back to zero point 0.1. It stuck there until about 5 minutes, and then 5.5 minutes it started to go down again. And the reason for that was that the water in the test tube actually froze. So while the water was freezing, there was no temperature change, right? And that's one of the questions we'll talk about later. Now this is page 16. I realize that as we get kind of further into the labs, the spacing gets a little wacky here. So this is normally just page 16, but if it ended up like this, it is what it is. There's a graph to make, right? So this says on a sheet of graph paper or using Excel, I'm gonna make a graph. Plot a graph of time versus temperature, it says. I'm gonna flip that again. I want temperature versus time. I'm gonna try to make relatively straight lines here. So I think I need to angle this just the tiniest bit. And maybe I shouldn't because it's gonna throw me off. Alright, so I said relatively straight lines. It's a little angled, but it'll do. So I have temperature here. I have time here, right? So I would go, my time scale is going to go 0 to 7.5 minutes. So 0, 30, 60, 90, 120. And it's gonna just keep going, right? Time in seconds. Temperature is going to be in degrees Celsius. So my highest temperature was, I've already forgotten. But I can scroll over. It was 22.1. My lowest temperature was -5.7. So I'll go to 23 and I'll go to -6. Right. There is no rule that says the bottom of your y-axis has to be 0. So I'm going to make it -6. I'm going to make this 23. And I'll just, I would have a scale in between here. 0 is probably close to here. -2, -4, right? Let's make the top 24 just so it's even numbers. 24, 22, 20, 18, and so on, right? So my first temperature would be at 0 would be 22. My next temperature I think was 7. So 7.1 and then 1.2. So 7.1 would be about here, 1.2 would be about here, and then I'm at 0.1 for quite some time. I do have that little blip at 0.4. I go back to, or negative 0.4, I go back to 0.1, and then it goes down again, right? And said to connect the dots, so right, it'll look kind of like that. I have that little blip, and it goes back up, it goes down again, right? So this kind of looks like, if I make kind of more of a best fit line, it might look like this, right? So on the graph, label where freezing occurred. Well, this segment here, where the temperature basically doesn't change, and maybe if I wanted to be clever, I might even say all the way out to there. There's where freezing occurred, right? I know that because the temperature stopped changing. Based on the data, what was the freezing point of water? So my question number 1, based on my data, if I look at this, the freezing point of water was almost certainly 0.1 degrees Celsius. It's very close to 0, which we know it should be, which is reasonable. How do I know? So the freezing point of water based on my data is where the temperature stopped changing. How do I know? I know that specifically because the temperature stopped changing. During a phase change, we have 0 temperature change, right? Should there be a temperature change while the water is undergoing the phase change of freezing? No. Can you determine the melting point of ice based on your data? Explain. Well, if I read this way, it's a cooling curve, so I'm cooling down water, I get it to freeze, and then I cool down the liquid. If I take it and I flip it around, it means that I would start with a solid. I'm adding heat. I get it to change from a solid to liquid, and then I heat up the liquid, which means that I can absolutely determine the melting point of ice based on my data if I read the diagram, if I read this curve backwards, because then it would read as a heating curve, and freezing and melting happen at the same temperature. They are opposite phase changes. They will occur at the same temperature. Finally, number 4, what happens to the kinetic energy of the water sample while it is freezing or undergoing any phase change? How do you know? Give proof from your data or proof from the graph. So what happens to the kinetic energy? If I had worded this average kinetic energy, would be much simpler of an answer, or much more obvious of an answer, I should say. What happens to the average kinetic energy of the water sample? It remains the same. How do you know? The temperature remains the same, and temperature is a measurement of the average kinetic energy of the particles in an object. Give proof from my data or my graph? Well, here, all of these points where I am still at 0.1 degrees, again, kind of disregarding this negative 0.4, it's an outlier. But all these points where I'm trapped at 0.1 degrees Celsius, that is showing that the average kinetic energy is not changing. That's showing that the temperature is not changing. So there is evidence, there's proof from the data, right? This lab was mostly just to help you see, create your own graph, create your own little chart here, recognize that freezing is something that happens from a liquid to solid, but there's no temperature change, right? This was a physical, like if you did the lab or you watched me do the, it was very boring, but if you had watched me do the lab, it would have be sitting there, and even though the water was in the process of freezing, the temperature did not change, right? So no temperature change during a phase change. That was the biggest deal. All right, now this lab is due like on Friday, right? Plenty of time. It'll be due the same day as the test, just by the end of the day. Really just, you have the numbers now. You have the, we talked through the questions. You have to make your graph. So you do have to make your graph. Make sure you submit that with your lab. But other than that, this lab is fairly straightforward. We'll do the heat diffusion lab. We'll do another lab with the Bunsen burner in the near future. Until then, I will see y'all. Take care, kids.